This video in the Resources on Proof series is about proof using the contrapositive. So to use the proof by contrapositive, in order to prove that A implies B, you instead prove that not B implies not A using a different form of proof. You want to use this type of proof whenever you'd rather assume something about B than something about A. Say, B contains some complicated object that you'd rather assume about rather than deduce something about. It can be tricky to accurately calculate the contrapositive, surprisingly so sometimes. Let's look at an example of a theorem we can prove using proof by a contrapositive. So this theorem says that if n is a natural number, then if, when we divide n by 3, we get remainder 2, then n is not a square. So to use the contrapositive, first we need to calculate what the contrapositive is. So the contrapositive of this theorem is, if n is a square number, then n does not give remainder 2 when divided by 3. So the if n is a square number is not the things after the then in the theorem, and does not give remainder 2 when divided by 3 is not the things before the then in the theorem. Now let's actually try and prove that, the contrapositive, using a different form of proof, in this case, a direct proof. Suppose n is a square number. This means that there's an m that when squared gives n. Now let's examine n in terms of its divisibility by 3. So this is what the I and j are saying. If m is equal to 3i plus j, I is the number of times 3 divides m, and j is the remainder that you get. So j can either be 0, 1, or 2. So let's write this out. We have n is equal to m squared, which when we put in the i's and j's gives us that n is equal to something times 3 plus j squared. Now let's look at all the different values that j can take. If j is 0, then j squared is 0, and this means that n is divisible by 3. If j is 1, j squared is 1, so n has remainder 1 when divided by 3, and if j is 2, j squared is 4, so n has remainder 1 when divided by 3. In all those three cases, we do not have a remainder 2, and so we've created a direct proof for the contrapositive of our theorem, and so we can then conclude that our theorem is true. There's a written version of what you've just seen if you prefer to learn that way. We also have videos and written support available for the other different types of proof. Thank you.